Hello, everyone. Well, welcome to the lecture. So it looks like we're still expecting a few more people. So let's maybe start slow and then get to the actual lecture, like when we have more people showed up. So yeah, I hope you guys had a nice break. So Monday was Memorial Day, and we didn't have a class. It must be a nice break. I hope you guys took the advantage and made some progress on the homework. So the homework will be due next week. So if you do not have any additional late days available, like please try submitting on time. So in the last lecture, I mentioned the logistic note about the course evaluation. So this year, due to the pandemics, all the course evaluation will be conducted online. I said that you had received email about the an online form where you can submit your opinions about this course. Back then, that was inaccurate. So it turned out that I think they are only sending the email out like this week. I think you might have already received the email. So can I yeah, can anyone like verify that information? Oh, good. So glad to know that you guys actually received the email. So I think you have 1 or 2 weeks of time to complete the course evaluation. It will take you only a few minutes. So please go and click on the link and then submit your feedback about the course. Today we're officially entering our advanced topics sessions of the course. So none of the topics will be evaluated as part of the homework. But on the other hand, these are the very interesting topics that are closer to the state-of-the-art result and closer to the research world. So a lot of that a lot of things that we have taught and you guys have learned in this class are our foundations, our building blocks, and are also techniques about optimization, about online learning. And many of these techniques are still pretty much relevant in modern research world. And out of 100 papers on this topic, I think 70–80% of them will end up using bits and pieces of the same analysis and same steps and same techniques from what we have already covered so far. So so today we're going to revisit the topic that we briefly mentioned in the first half of the course when we were dealing with the first order optimization problems, and then ended up showing that the stochastic gradient descent is actually optimal in the general sense, because it actually covers a very large body of problems called stochastic optimization. Okay, say we want to minimize an expectation based on only the samples. So in those cases, the information theoretic limit or the statistical limit will kick in, which prevents any algorithm from getting faster convergence under the stochastic gradient model to get to the optimal solution faster than the standard SGE. Okay, but we also mentioned that in the typical problems that's of interest in machine learning, those that are in the form of a finite sum, you can actually design faster algorithms. So this is part of the modern literature where you can actually design sometimes exponentially faster algorithm to solve the finite sum minimization problem. And in this lecture, we're going to revisit this idea and then have a tour of some of the newer development in first order stochastic optimization. Okay. So this is backtracking a little bit from the last lecture, actually the last couple of lecture, when we were focusing on the new setting, the somewhat harder setting called the online learning setting, where the adversary will choose a sequence of convex functions for you to minimize, and at the end of the day, you want to design something that without knowing what to minimize a priori, and come up with a solution that behaves as good as like almost as good as the oracle, which knows all the function to minimize in day one. So over there we talk about several family of algorithms, including online gradient descent, which is very similar apparently to stochastic subgradient descent. And we talk about extensions of that to take into account of the different geometry of the problem via regularization. And then we talk about how to generalize the faster convergence or the logarithmic regret of the strongly convex optimization problems using OGD to a larger family of problems that satisfy so-called exponential concavity problem using an algorithm called quasi-Newton step. That was the topic of the last lecture. Okay, so to interpret this exponential concavity assumption, we can think about it as a restricted version of the strong convexity condition locally at every input point x, which says that the function needs to be needs to have curvature along the direction of the gradient. Yeah, so this should remind you of a weaker condition for linear convergence that we talked about a long time ago. That's called restricted strong convexity and growth rate condition. So these are related ideas. Although the exponential concavity explicitly talks about the direction being the gradient, and it's different at every local region. Finally, I guess we analyze the quasi-Newton the quasi-Newton update for the online Newton step, and then we established that you can get order log t regret for exponential concave functions, and the last thing that we talked about last time was computation, right? So since in online Newton step, every iteration involves something that's similar to a Newton step, where you have to invert a matrix and then apply to the gradient direction so that you get, in some sense, a quasi-Newton direction. And that, in the worst case, if you do it naively, it would cost order n cube complexity, when n is a dimension of your parameter vector. Okay, so but due to the special structure of the online Newton steps is presented, you can actually do incremental updates of the inverse of the matrix using the matrix inversion lemma, or also known as the Sherman-Morrison-Woodbury identity, in which case each iteration takes only order n square. Okay, so that allows a practical implementation of online Newton step with only n square computation in every iteration, which makes it a lot more practical. One caveat that I didn't get to mention at the end of the last lecture was that the Sherman-Morrison-Woodbury identity is notoriously bad for numerical computation. So numerically it's quite unstable. So if you keep doing rank 1 updates again and again and again, so maybe after 100 or 200 iterations, you'll end up diverging quite a bit from the numerical solutions that you would have gotten suppose you try directly solving the linear system of equation. In other words, so in practice, when you deal with the matrix inversions, sometimes you don't really want to represent the matrix inversion directly, but rather you want to represent some, say, Cholesky factors where you can keep updating with rank 1 updates and then recompute every once in a while to ground it, so that so that at the end of the day you don't blow up due to numerical instability. Okay, so this kind of issues are quite common when you are implementing these numerical algorithms. So you have to appreciate the fact that the finite computer is with finite accuracy. If their exponential blow up in some regimes, then it can creep up pretty quickly when you chain the computation together, and the error will compound exponentially as the number of times you apply those computation again and again and again. Okay, just in case you run into some mysterious bug when implementing this rank 1 updates in the future. Well, so I wanted to say a few more things about the topic of online learning. We covered quite a bit, but there are a few chapters that we didn't get to cover in this course. So that includes, so mostly we were dealing with the full information feedback, where in every iteration we are getting the exact gradient of that individual function that we receive at our chosen point. So sometimes we don't get to see that gradient. Instead, we only get an like zeros order feedback in the form of a in the form of a function evaluation at this chosen point. Or sometimes we even only get the stochastic approximation, or we only get a feedback that's in expectation the same as the function evaluation. In those cases, these problems are called online learning problem with banded feedbacks. We didn't get to talk about it at all, but there's a very interesting chapter that I did cover in the last time this course was offered. And you can look at that chapter in the Elad Hassan book, where there's an interesting approach to the reduction approach to just directly apply the full information OGD for solving the bandit problem with a very interesting one sample stochastic approximation of the gradient using only a noisy objective function evaluation. Okay, so if you somehow randomize your chosen points, then you can actually get away with estimating a d-dimensional object using only one-dimensional information by blowing up the variance for a little bit. And things gets more interesting. Suppose this you're trying to query a gradient that's closer to the boundary of the feasible region. We call that in OGD we're doing projected gradient descent. So there is a feasible region. So when you get to the boundary of the feasible region, then the standard approach of doing this kind of approximation can't be used. So think about it as a clever implementation of the finite difference approximation of the gradient. And then like what we talk about when we deal with the Newton's method and when we deal with the interior point method called log barrier or log determinant barrier. So those are self-concordant functions starts playing a role. So there's a very extensive theory for the bandit problems on how you can apply the calculations you get from OGD to actually solve those problems. And sometimes when the projection is an issue, so notice that when the convex set is general, then the projection can actually be the most computationally expensive part of the entire process. Okay, so in that case there is a chapter about conditional gradient methods or Frank-Wolf methods where it allows you to for some special cases of the convex set like simplexes, a convex polytope defined by spanning vectors like nuclear norm, balls, and so on. So in those cases, you can actually use an old algorithm from the 1950s called Frank-Wolf algorithm to make every iteration of the algorithm significantly faster. Okay, that comes with a slight cost in how quickly you can converge in both the batch optimization setting and in the online learning setting. So I encourage you guys to look at it if you have interesting problem settings where the projection is the limiting factor. And finally, so this is related to a question that I received in the last lecture and also on PSR on why on earth are we only comparing to a fixed a comparator in the hindsight, right? So the objective function can change over time. Like suppose we only compare with something that's fixed, then that seems quite unfair since the algorithm is allowed to choose a different argument in every iteration. Okay, so this is related to how can online learning algorithm adapt to changes in the concept and adapt to say maybe a sequence of comparators that changes slowly So there are various formalization of this idea of adaptive online learning, which is really a very hot topic nowadays. So some of my PhD students are working on related problems in this vein. So in the last lecture of this course, today's the 17th, so in the 19th lecture of this course, so that will be the end of the course. I will choose one of these three topics and then cover with some additional details than what I've already described here on this slide. Okay, so before the last lecture, so consider this slide as a mini summary and as my effort to wrap up the discussion on online learning. And now we are back to optimization. Okay, so we're back to solving a static optimization problems that you are given, but let's try to do it better than what we have done previously. All right, so it's been a while, so let's have a quick recap of what we know about stochastic algorithms for solving, say, problems that are quite common in machine learning and statistics of this form, right? So when your objective function to minimize can be decomposed into a summation of n items, and each item could be coming from one of the data points. Okay, so beware of the notation. So now n denotes the size of the data set, and the dimensionality of x is unspecified. So you can call it r to the d. It can also be just a function. Okay, so in SGD, we're doing stochastic approximation of the gradient. So instead of moving towards a gradient direction, as in the full gradient descent, we're now moving towards the negative of the approximation of the gradient, where this index I of k is chosen uniformly at random. Okay, when you do that, so it's clear that condition on xk minus 1, then this stochastic approximation is an unbiased approximation of the full gradient. So if you take the conditional expectation, you recover the full gradient. So hopefully, as we move in the direction that's approximately correct for many more iterations, the variance will somehow cancel out, and the randomness will become certainty, and we end up converging to the optimal solution deterministically. So so we've done a lot related to analyzing the convergence of these iterative algorithms. And then like these convergence results are specified with specific rates of computation in terms of how many iterations you need to run, and with given k iterations, how where you can get what is the property of the solutions that you'll end up getting with a budget of k iteration. Okay, so that's specified for each family of optimization problems that we can talk about. So for general convex optimization, that can potentially be non-smooth, but needs to be Lipschitz, then we can establish that the gradient descent and stochastic gradient descent both converge at 1/square root of k at a very slow sublinear rate, or equivalently 1 over epsilon square iteration complexity. So suppose we further assume that the gradient is Lipschitz, or the objective function is strongly smooth, and then we can end up improving this from 1/square root of k to 1/k in gradient descent, but not in where you have stochasticity. Okay. Further, like suppose we add strong convexity in addition to strong smoothness, then we can get an exponential improvement and achieve a linear convergence rate. So it is linear because it is linear in the semi-log plot. So when we take the log of c to the k, then you get something that's linear in k. With c, and in this case, c is strictly smaller than 1. In particular, c is something that looks like 1 over m divided by l, right? C is roughly you can take C to be this with an appropriately chosen learning rate, where M is a strong convexity parameter of the function, and L is a strong smoothness of the problem. In the full gradient, you have exponential convergence, exponential improvement over those without strong convexity. But the stochastic approximation, it does improve, but it improves very only a little bit. Okay, so we proved this result with additional tilde here. By using a reduction approach to online gradient descent, and then just apply the regret bound. But there are analysis that allows you to get rid of the additional log k term. Okay, so generally speaking, for the SGD, you can get like order 1 over k for the strongly convex case, which matches the lower bound. But this is quite a big gap between these two, right? Between both these two. So we don't actually see significant improvements for stochastic gradient descent when even we are willing to add additional assumptions. Okay, so one of the key reasons behind this phenomena is that in stochastic gradient descent, we cannot actually take a constant learning rate. Instead, we have to take a learning rate that's somehow diminishing, so that the randomness that's coming from the stochastic approximation of the gradient will slowly get averaged out as we move further into the optimization process. So that's a high level reason why this is the case. Okay, and then we had this slide at the end of the SGD lecture by saying that, well, there's a lower bound, but it is end of the story. So in the modern literature, so it becomes more common to directly work with the so-called finite sum problems, where instead of having an infinite sum in a form of for instance an expectation when drawn from some distribution, if we work with a finite sum, and then there are additional information that we can leverage, and in particular we can somehow reduce the variance of the stochastic gradient by coming up with better stochastic gradient approximation than simply picking a random, by simply picking a random index and evaluate the gradient there. Okay, so if this is the only thing that you remember from this lecture, and that's perfectly fine, is that like for finite sum problems, then we can essentially achieve the same convergence guarantee of the gradient descent, but then every iteration takes only one incremental gradient call rather than a full gradient call. Okay, so you do get improvement from 1 over square root of k to 1 over k when you assume a strong smoothness, and you do get the exponential convergence. Suppose you suppose you in addition assume that the whole thing is strongly convex. Okay, so that's that's the topic. So formalizing that and illustrating how this algorithm works is going to be the topic of today's lecture. Okay, so yeah, if there are any questions about, I hope that this recap like helps you to remember some of the things that we talked about in earlier lectures. If there are any questions, if there are any part that's unclear, like please just type into the group chat, and I can respond to them like right away. Because if the story is not clear, then some of the materials that we're going to be talking about is not going to make too much sense to you. Okay, so what we're going to do is to introduce the algorithms. We're going to be talking about some of these fast gradient methods, mostly based on the idea of reducing the variance. And then we're going to also be illustrating like some other tricks that can be used for modern stochastic optimization, including momentum and acceleration. And then we'll end the lecture by describing a family of other algorithms that tries to in some sense adapt to the geometry. That's pretty much similar to the idea of the follow the regularized leader, where you want to come up with some kind of regularization and then like do the gradient descent with the right geometry. Okay, so let's start with the very first groundbreaking algorithm that solves the stochastic optimization problem with much faster convergence rate. Okay, so this algorithm is called stochastic average gradient. So notice that we talk about ASGD, so this averaged stochastic gradient descent, which adds this averaging trick to SGD, but that's not the same as a SAG. So SAG appeared in 2013, and the idea is the following. So instead of just calculating the stochastic gradient and move towards the stochastic gradient direction, it uses more space to maintain the individual gradient of every individual function. Okay, so notice that f that you want to minimize is of this form. Okay, so you want to maintain the gradient at of each individual function and call that the vector gi. Okay, so the algorithm goes as follows: you initialize your algorithm at your favorite location, and then and then you calculate the individual gradient for every data points. Have every segment of your objective function value, right? So instead of adding them up, you are keeping track of each one of them. And in every iteration, so the simple algorithm would pick a random index, and then basically just update update the gradient of that corresponding location. Okay, so you basically pick one and then update the update this GIK, pick this random coordinate and update the that to be the incremental gradient that's calculated on an updated parameter. Okay, and yeah, you don't have to change anything else. And then in every iteration, so you basically move towards the direction that's given to you by the average of this incremental gradient from previously. Okay, this sounds like a reasonable algorithm, but it's also a little bit like weird in a sense that it's nothing like what we have seen before. Okay, so if we just inspect this algorithm, so this is a this direction that we are moving towards is not in expectation the average gradient, not in expectation the correct gradient, and well, the randomness of this thing is quite complicated. So notice that in every iteration we're choosing a random index and then update the parameter with just that index of this GI update, right? So if you take expectation of this thing, so I don't even know what you're gonna get, and it's definitely not the gradient at this location xk minus 1. Okay, so in some sense the SAG is a biased gradient based algorithm. But besides the blow up in the space complexity, which you now need say order e times n space, can anyone like point out whether you can implement this algorithm like with the same time complexity as the stochastic gradient descent? Like it seems like you need to do a summation in every iteration, but can you actually do better? Anyone? Trying to ask these questions while you look at an algorithm can help you to understand the algorithm better. So this is just a simple test of your understanding of whether you have understood how this algorithm works. So anyone, if you okay, there's an excellent answer from Hoja. That's excellent. Like you only need order D or even just order number of non-zero elements to update to update the summation. So you can basically just keep track of the summation together with a big table, and then yeah, all these are great answers, and then add and subtract this individual gradient calculated at this location and at the previous location. So you subtract this, you can get order one access to this since you kept track of the full table, right? You can keep track of the overall average, and then you basically add and subtract the differences, and that's like an order D update, right? It doesn't depend on N at all. So this algorithm is no longer unbiased. It has extremely low variance. So the variance is as low as 1 over n squared. Notice that you have this 1 over n term that's over here. Well, and computationally you can implement it just as efficient as SGD. Okay. So it turns out that you can show that under this additional assumption that each Fi is strongly smooth with a parameter L. Okay, so notice a subtle difference from the standard assumption on the strong smoothness of SGD of the general optimization problem, where we assume so in gradient descent, the assumption is that gradient of F is Lipschitz. So here we are assuming that every individual Fi is Lipschitz, which is stronger, but not a crazy assumption that's always violated. So you almost always have this assumption true, but the parameter of the Lipschitz constant of the overall F might be different, might be smaller than the constant L here. That's required for every individual Fi. Okay, and now let's maybe denote this x bar k as average. So we're doing the averaged SGD's averaging trick. So suppose we do the averaging and then invoke say the convexity, saying that the average point is not a bad point to output as a final solution. And then if you take the learning rate to be a constant learning rate that's qualitatively the same as that of the gradient descent, then you'll end up getting a convergence on the order of 1 over k. Okay, do take note that there are some subtle differences here. So this is the same as the gradient descent, at least up to a constant. On the other hand, this one is also 1 over k, but there's an additional constant here that depends on that's linear n. Okay, so when n is huge, then this term might be the dominating factor, and it's not necessary that sag is much faster than gradient descent. Okay, so notice that the complexity of calculating the full gradient is only proportional to n. So having an n here seems to be defeating the purpose. But all is not lost. There is a trick that allow you to get around with not suffering the factor of n, right? So you can basically choose your initialization point carefully by running like a one-pass SGD. So that doesn't add to the complexity, overall complexity at all, but it reduces your like a suboptimality to something that's on the order. Like it reduces the suboptimality to something that's on the order of 1 over n or 1 over square root of n, which cancels out with this n. So ultimately, you get a fast convergence when you are closer to the optimal solution. Okay, so this is a trick that's useful in theory, but it also have a significant effect in practice. Okay. Yeah, there's another thing that of course you can also show that the result holds for the best parameter vectors that you've gotten so far, but the average iterate is something that's more easily implementable in practice, which does not require you to evaluate the objective function in every iteration. Okay, so how about if we add strong convexity? Suppose we, in addition, assume that the overall the overall function is strongly convex. Yeah, actually, so they're assuming that the individual function fi is strongly convex with parameter m. So this seems to be a significantly stronger assumption than what we had before. It can be realized as follows. So suppose you have this 1 over n, I from 1 to n, fi x, and then you add say a regularization term, half m x squared. So you can essentially distribute this half m in n copies, and then you can rewrite this as I from 1 to n fi x plus say I guess half m x squared by putting it in the bracket, and then call this function fi tilde, which is actually m strongly convex on every individual component. And the sum of n folds of f, you divide that further by 1 over n, so it ends up giving you something that's right. Still, so if you hope that this f tilde is a good approximation of this original fi function, then this m should be chosen to be a relatively small number, right? So so I guess a typical number that you can choose for m might be like 1 over square root of n, or even 1 over n. Okay. So what you can get in terms of the convergence guarantee of SAG on the both the strongly smooth condition and strong convexity condition for every individual segment fi is the following. Okay, so you get some kind of constant and that measures the initial condition and how far away you are from the optimal solution in both objective function value and then in the argument. And then as the number of iterations gets larger, you get exponential convergence. Okay, in the form of this is order c to the power of k when c is roughly proportional to the same 1 over m over L. Like so there's some additional restriction on this shrinkage factor, in which case it doesn't. Like even if m is significantly larger and m over L is like a constant, you do not actually get the get a benefit because there's another hard limit that's on the order of 1 over n. So it suffices if you choose m to be like supposed to add this additional regularization term to make it smoother, to make it more strongly convex. It suffices to choose m to be proportional to 1 over n. Okay, so this is a huge improvement actually. It improves exponentially and it matches the convergence result for I guess nearly match the convergence result for the gradient descent. And another thing to note is that Well, the choice of the learning rate doesn't really depend on the strong convexity parameter. So it's possible that the SAG can have linear convergence in the cases that are weaker than strong convexity, and in the cases when we do not have when the function is only locally strongly convex near the optimal solution, or maybe even strictly strongly convex near the optimal solution, or even just to satisfy some like a weaker condition such as the Polyakh-Lojasiewicz condition. Okay, so under those conditions, it might be possible to show that SAG also converges exponentially. And the analysis of this convergence bound is in fact highly non-trivial. So this comes as a paper that's groundbreaking, but nobody is able to check their technical results. So the proof is extremely long, and it's not just long. If it's just long and tedious, then people can go over it, and with a couple of graduate students, and it's easy to check a 15-page long proof. But their proof is actually computer aided. They have to show the existence of a certain points and the existence of a solution in a semi-definite program to certify the existence of the learning rate. So it's a very intricate proof that they put together to establish this strongly convex convergence bound that goes to zero exponentially. Okay, so yeah, feel free to take a look at their paper, and you'll be surprised how much details that they need to get into, and how much more complicated that this proof is comparing to some of the other proofs that we have seen in this class. In practice, however, this is an algorithm that actually works quite well, and it significantly improves over the standard stochastic gradient-based method. So on the plot, I'm showing the same old logistic regression that we've been using as an example throughout the course. and the red line are the average performance of the stochastic gradient, where all these seemingly very noisy curves, so those are the 30 different realization of the stochastic gradient descent algorithm. So sometimes it does pretty well. In other times, like it can blow up quite badly. And on average, it converges reasonably well, but you see a lot of randomness in this convergence. And it's not like getting the suboptimality significantly close to zero, even after many iterations. On the other hand, if we look at SAG, like I guess yeah, like this part of the curve makes it a little bit weird that it doesn't give you linear convergence. But notice that this is logistic regression, which doesn't necessarily satisfy the strong convexity parameter being strictly greater than zero. So what we are looking at might be like a convergence of SAG that's linear initially, and then it switched to this 1 over k convergence that's sublinear, but still much faster than the 1 over square root of k convergence of stochastic gradients. And it's interesting. It's the interesting property of SAG is that it has extremely low variance, that with over 30 runs, and each run is essentially identical, despite the randomness in the algorithm, where we choose every update with the stochastic sampling of the different coordinates. Okay, so so some notes about this experiment. So we actually have to take one full cycle of SGD before starting the SAG. Because other than that, like SAG doesn't seem to get to any solution with a given budget of number of iterations. So these algorithms are useful, but sometimes their bounds do reflect the reality, and you have to like optimization and is an interesting area where the theory and practice are actually quite close to each other. But using the like one pass SGD to initialize the SAG actually work like a charm. Like tuning the step sizes for SAC is also like not the easiest thing to do. So perhaps the SAC can benefit from some kind of adaptive choice of learning rate using ideas like backtracking. I think Ryan, who put together the set of experiments, like he communicated with Mark Schmidt and also other authors of SAC, and then they agree with this evaluation that SAC is sometimes a bit like sensitive to the learning rate choices, but for convex problems and for strongly convex problem, like when you manage to choose the right learning rate, like all the other like later and arguably more easier to prove modern stochastic gradient methods do not actually perform as well as a SAC. So we'll see one example later after we talk about SAGA. Okay. So so SAGA is an extension of SAC that is actually very similar, but it makes one very subtle changes somewhere. So again, it still maintain a table containing the gradient, and what it does is the following. So it still picks the random index in every iteration and then update this particular column of the table into the new gradient, and it still calculate this in some sense a snapshot, which makes use of everything from the previous iteration, but then add and remove one individual. But the one that you add and remove is not actually adding and remove like one particular coordinate before you take the average. You take the average of the previous snapshot, and then you move along the direction that's that basically you add something without the additional coefficient of 1 over n. So recall that in SAC, we are doing, it's equivalent to doing 1 over n GIK minus GIK k minus 1. Okay. So this 1 over n factor is gone in SAGA. So that's the only difference from SAC and SAGA. So what's the benefit of this new approach? That's similar to SAC, but it's doing something that's slightly different. So you can actually show that when you use a SAGA's gradient estimate, so it produces an unbiased estimator of the gradient. So let's do the simple calculation to verify that. So if we take the gradient expectation of IK, so recall that IK is a random variable. Okay, since IK is a random variable, IK is the only random variable that we take in this expectation, drawn from uniform 1 to n. Okay, so this is a fixed constant that doesn't depend on IK. The first term gives you the unbiased estimator of the gradient, since we're choosing this IK uniformly at random. So you get 1 over k, the gradient of Fi at this new location. Okay, the second term, when it computes the gradient at the previous iterate, right? So the second compute the gradient at the previous at the previous iterate, right? So notice that this is always this most recent gradient of sk minus 1, where the most recent gradient of f for that coordinate ik, right? So if you take the expectation of this over ik. So notice that this is just one of the summands here in this system of summations. With probability 1 over n, you're picking one of these coordinates from I to n. So the expectation of the second term is actually just the same as the constant that we decided to ignore, k minus 1. And then plus 1 over n, I from 1 to n, gi k minus 1. Okay, so these two got canceled out, then you end up getting an unbiased estimator of the gradient. Okay, so this trick of adding and subtracting something to your stochastic gradient estimate is commonly used as a trick for variance reduction. So if this GIK k minus 1 is highly correlated, positively correlated with GIK, then this can significantly reduce the variance. Okay, consider this slightly more general estimator of the following form. Okay, so you are subtracting y and adding the expectation of y back. So when you know the expectation of y, you can do that without incurring additional computation. And then you can work out that when you take the expectation of this theta alpha, then you get the interpolation between the expectation of x and the expectation of y. So in our case, we are choosing this alpha to be 1, in which case you recover the expectation of x. So how about the variance? So for the case when alpha is equal to 1, so the variance, you can do the calculation here. The variance is only the variance of x and y, and using the variance formula, and notice that x and y might not be independent. Otherwise, the third term is 0, and you don't really get any benefits. But suppose x and y are positively correlated, then this covariance matrix is not negative. Then you can reduce that part of the variance from the marginal variance of x and y. Okay, so this trick is used everywhere. So in the context optimization, this is called variance reduction for the stochastic gradient estimate. In control and in the reinforcement learning, similar techniques are called control variate or called W robust estimation. And W robust estimation also appeared in much earlier in their original context of doing causal inference and doing causal effect estimation. And it's a statistical trick that has a very old origin that dates back to the very early days of the development of these the mathematics of statistics and probability. Okay, so so in some sense, so both Saga and SAG, they get a benefit of a reduced variance due to the fact that of the negative correlation. And SAG in addition gets a benefit of variance reduction by choosing this alpha to be something that's much smaller. In which case the SAG will have 1 over n square factor smaller variance than Saga. Okay, so what the Saga is leveraged upon is really only the benefits of the positive correlation between x and y, where SAG leverage upon something more, like from the algorithm. So I still find SAG a really weird and really peculiar algorithm, like even though it works extremely well in practice. Okay, so in theory, Saga matches the convergence rate of SAG in both cases. In both the case when we only assume that the function is smooth, and in the case when we assume the function is strongly smooth and strongly convex. But the proofs are much simpler, thanks to the fact that Saga has unbiased gradient. Okay, so in practice, if we look at the convergence plot by adding Saga into the picture, you see that Saga is similar to SGD in the sense that it's highly varying. So it has a much so it has a much higher variance compared to SAC, and different run can yield very different solutions. So of course, that kind of problem can be readily solvable using this by outputting the online averages of the sequence of optimization solutions. But still, if you just look at the trajectories of the objective function of every individual iterate, then you see that the saga has a much higher variance and have a comparable convergence rate and convergence curve to SAG. Okay, so there are papers out there about a more detailed empirical evaluation about these modern gradient-based methods for both convex optimization problem, for structural SVM, for tagging tasks, and name entity recognition, and so on. So these are fundamental problems in natural language processing, and also for, say, computer vision tasks like denoising, deconvolution, and so on. Okay, there are also like empirical evaluation of these methods for non-convex problem for learning deep neural networks, but those are the cases that often you do not actually see a clear-cut improvement of these methods over the standard SGD. So some notes about the experiments that I have shown you. Doing a warm start with one pass SGD helped both SAG and Saga significantly to have the nicely looking curves that I've shown you in the previous slide. Like in terms of tuning the learning rates, it's observed that Saga is less sensitive to learning rate choices. It's slightly better, like more stable, like for some reason compared to SAG, and it's comparable to the difficulty of tuning learning rates to the standard SGD. So let's move to the next slide. So SAG and Saga are not the only algorithms that's out there that achieves the faster convergence than SGD for finite sum problems. So the idea has been revisited a lot, and there are many different algorithms that had been proposed. Here are some typical examples of them, which include this SDCA. So this is stochastic dual coordinate descent. So these are applied to, I guess, a more specialized family of problem where you can calculate the dual, and since the primal are of a summation form, then the dual naturally will have a coordinate separated format with a coordinate separated constraints. So SDCA leverage this fact and then solves the problem in the dual. And then you basically randomly select a coordinate and then do coordinate ascent for that direction. It turns out to be like very similar to the Saga update if you convert those dual update to the primal. The advantage of doing SDCA for those problems that are applicable is that you get an estimate of the duality gap for free, which can be used as a principled way of certifying when to stop the optimization. There's a more popular approach of doing the variance reduced stochastic gradient descent for finite sum problems called SVRG. So this is a stochastic variance reduced gradient method. So we'll talk about this algorithm in details in the next slide, and hopefully after we take a break, we'll be able to sketch out the analysis of this algorithm and figure out how like these groups of methods actually leverage upon the reduced variance of the gradient. So the proof of SVRG is the simplest, and is arguably also the most transparent on how they rely how it relies on the reduced variance of a sequence of gradients. Okay, there are like also many other further extensions that add, say, projection as a proximal operator so that you can now handle the composite optimization when the smooth part decomposes into different components. There are other approaches of doing that, which that uses things like homotopy methods that keeps introducing a smaller and smaller strong convexity parameter in the end, and then do like the simple like more simple stochastic gradient descent. There also work on adding acceleration to these methods. So far we've only talked about the non-accelerated version of this problem. So adding acceleration to this can further improve the dependence on the condition number and improve the linear convergence rate, improves the parameter C in that linear convergence rate of C to the power of K. Okay, so there's a huge body of work on modern gradient methods nowadays. Okay, so still I'd say that the main point of reference, suppose you want to get into this field or understanding or you want to understand this line of work with details, then the SAG and SAGA papers are really like the first thing, where the original idea was from is the paper to read. And in terms of the proof, and the more easily extendable version of the proof than SVRG is the version to look at. Okay, so we'll take a break and we'll resume at 2:09, and then we'll come back and talk about SVRG, and then talk about analysis of the SVRG that establishes the exponential convergence. All right, see you guys in a little bit. All right, it's 2:09. Welcome back to the lecture. Yeah, I just realized that I forgot the new every lecture routine to talk about the background. Okay, so this is a world tour that continues to far and beyond. Well, so before I start this lecture, it was 30 minutes before the NASA and SpaceX was to launch this Dragon spaceship into the International Space Station, carrying 2 astronauts. Yeah, that's a really exciting move for the U.S. to take, and for the private company to take the initiative of reducing the cost of space travels and so on, for the final mission to um, maybe create a human habitats in outer space, perhaps in where my background is. So this may really look like maybe Arizona or somewhere in a desert area of the United States. But it's actually the footage that's sent back by a Mars rover. So it's actually Mars. It looks very much like Earth, and it has a lot to be explored there. And hopefully in the yeah, Alex managed to guess it. So hopefully in my lifetime and in your lifetime, we are able to witness the mankind like at least taking the move towards landing a person on Mars. It'll take many years before anyone to start from Earth and get there. But yeah, taking the move and embarking on the space travel is uh, something that I can foresee that maybe we're able to do in our lifetime. And hopefully by then, like simple space travel to the moon might be even affordable to ordinary people like you and me. Okay, back to the lecture. Yeah, actually, a lot of the space travel and like the corresponding algorithm and technology rely on a careful engineering of the control systems, and the aerospace expedition is in the entirely vacuum, and that makes a lot of the theoretical assumptions and mathematical assumptions more easily satisfiable. Therefore, like when we talk about something being engineering, when we talk about um, some paper, some algorithm being very engineering, so often that's like a negative comment. But in the old days, at least in where I was getting my education from, I think engineering is actually an extremely positive word that says that you need the precision and you need the guarantees and you need the mathematical proof that this is actually going to work. So that's what happened in when you send a rocket to the space, and that's when the robust control and optimal control start to play a role, and a lot of those algorithms behind the scenes comes with strong mathematical proof of guarantees. Otherwise, how are we able to bet our money and life on expeditions like this into the unknown territory? Okay, so hopefully machine learning and AI is going to play a more and more significant role in our adventure as mankind. Okay, back to the lecture. So let's talk about SVRG. So first, let's talk about the algorithm, and as we can see, the update seems quite similar to Saga, with a critical difference. Okay, so Saga maintains a table of all the individual gradients that's calculated at some point in the recent past. On the other hand, SVRG uses, in some sense, a snapshot G tilde, which is an actual gradient of the full objective function at some location called X tilde. Okay, so and then like you add and subtract the individual gradient with a randomly sampled IT at xt minus 1, and you add that, and then you subtract the corresponding individual gradient at the previously snapshotted location. Okay, so so there's an obvious computational benefit here, because we no longer need to keep track of the full table of individual gradients at every data point. So all we need to keep track of is x tilde, which is in RD, and well, this G tilde, which is in RD as well. So you only need to order D space, and each update is order D time. So essentially, we're not losing anything compared to the standard SGD. Okay, so you do need to double your incremental gradient calculations if you adopt this approach, because you have to recalculate the gradient at a previous location, which you have already calculated before. Okay, you have to do that each time you update. But it seems like it's a good trade-off by introducing a factor of 2 in time and then reducing a factor of n in space. Okay, so SVRG works unlike previous approaches. It works with outer loop and inner loop. So in the outer loop, which is indexed by S, every once in a while of these updates, you recalculate the full gradient as a snapshot. Okay, you keep this x tilde, and then you keep the corresponding full gradient that's calculated at x tilde. And then you enter the inner loop. In the inner loop, you run many iterations, and each iteration is a stochastic update, where you randomly sample a position, you randomly sample a data point, and then you construct, again, an unbiased estimator of the gradient, but with a reduced variance, thanks to this snapshot. Using the same trick that we've seen from Saga, it's clear that this is an unbiased estimator of the gradient. And then like you do this iteration of inner loop for a pre-specified number of iterations, capital N, and hopefully that inner loop is going to reduce the objective function value, say by half relative to the optimal objective function value. Okay, and finally, after you're done, you set the next snapshot. So this is a like technicality, but you actually choose the next snapshot like uniformly at random from 0 to n minus 1. Okay, you can alternatively choose it to be the last one. But the analysis of SVRG covers the case when you choose this x tilde s to be a random coordinates that's a random coordinate that's selected during the update. So again, notice that this doesn't actually improve. It doesn't actually increase the space complexity, because this is something. This randomness is something that you can calculate well ahead of time. So so you toss a random coin and figure out that this magic number t is 76. Then when you hit 76, you basically keep that coordinate, and in fact you can stop right there, right? Because it doesn't make sense to keep updating further. In terms of the convergence, since this is an inner outer loop type of algorithm, so let's measure the convergence in terms of the number of outer loop. So in terms of the S, you get C to the power of S. Okay, you get a convergence rate that looks like that. That's a linear convergence rate. So essentially, every n iterations in the inner loop would reduce the objective function value, reduce the suboptimality by a factor of 2/3. Okay, so you can also make it more comparable to other computational guarantees that we've seen by rewriting this in terms of the total number of incremental gradient oracle calls. So that's the total number of evaluation of the individual gradients. So then you'll get still the linear convergence given by the log 1 over epsilon, and then you get the well-expected factor in front. This is saying that you need n plus L over m number of like inner loop iterations before you manage to reduce the suboptimality by half. Okay, so like the idea of the convergence proof of SVRG is essentially leverage upon the reduction of the variance. So as t gets larger, the variance also goes to 0. So notice that this is quite different from SGD when the expectation of this gradient approximation T is like the only upper bound that we have about this is I guess a sigma square plus G square, right? So when this is the only assumption that we have, then we cannot get faster rate. But suppose you are able to show that the variance is reduced. In particular, as t gets larger, then the variance of the stochastic approximation of the gradient gets smaller. Then you should be able to achieve faster rates. Okay, so we'll see how this convergence proof works in the next 20 or so minutes. So let's move to the board so that we can. All right. So convergence of SVRG for L Lipschitz Fi and M strongly convex. Yeah, so notice that the strong convexity parameter here, you can actually, for SVRG, you can get away with a slightly weaker assumption on the strong convexity, because strong convexity parameter only applies to the to the summation rather than the individual components. Okay. Yeah, in that additionally added strong convexity doesn't really make a difference, but over here, like you get away with a different type of split. Okay, and let's say that what the algorithm is. The algorithm says that we are in the inner loop. We are updating currently the snapshot is x2, then we're updating the parameter x t plus 1 is equal to xt minus, well, let's use our standard index, xk plus 1 equals xk minus the learning rate t, and the g, I guess a randomly chosen index ik at the location k, subtract the gik at location x2, and then plus 1 over n sum of the individual gradient at x2. Where gi is defined to be the gradient of fi. Was it a question? So, okay, never mind. Okay, for simplicity, let's call the whole thing. Let's call the whole thing v. Okay, vk. Okay, just define this as vk. Yeah, so that we can use the same steps that we've learned before to start the analysis, and then we'll invoke a specific property related to vk after the fact. All right, so let's start as usual. We in the analysis of the gradient-based methods, we want to somehow make use of the algorithm and then try constructing some kind of a telescoping structure. So by just applying the algorithm, we get xk minus t and v k minus x star, where we denote x star to be the arc mean of the objective function. Well, by this simply is follow from the algorithm. So let's expand it, and we get xk minus x star square minus 2t xk minus x star transpose vk plus t square vk square. Okay, so as usual, we take the expectation, take the conditional expectation, conditional xk. Okay, and we get yeah, I guess conditional on xk and everything in the past. So vk is also fixed. In particular, x snapshot x tilde is also fixed. So we get the xk minus x star norm minus 2t. So notice that we've established that vk is an unbiased estimator of the gradient. So we get the gradient of f. Okay. Right, plus t squared, the expectation of vk square given xk. All right, now by the definition of convexity, by the definition of I guess convexity, we can replace the middle term with objective with the difference in the objective function. Replace that with suboptimality. So this is something that we've done for many times. Now we need to somehow bound the last term, right? Since this vk is not a stochastic approximation of the gradient that's standard, so we need some new tools here. So let me introduce a lemma, which we're gonna be applying here, and then we'll leave the proof of this lemma to later. So this lemma can be thought of as a variance bound of vk. Yeah, so instead of bounding the variance, it's actually bounding something that's stronger. So it bounds vk 2 norm square to be smaller than 4 times L times fk minus fx star plus fx snapshot minus fx star. Okay, so let's state this lemma first. Okay, so so notice that this lemma realizes the what we said. Realizes what we said here, that the stochastic gradient goes to 0 as t gets larger. So this is exactly what it is saying. So suppose the algorithm converges and xk and x tilde, they will all be closer and closer to the optimal solution. Therefore, the right-hand side of this inequality will go to 0. So if this is a convergent sequence, so in some sense, this is a trick that allows you to bound what you are trying to bound and then use it to control the variance, and then in some sense the feedback loop allows you to achieve an iterate that leads to faster convergence. But now let's assume this lemma is true and then substitute this lemma into as an upper bound into here. Okay, so we get plus yeah, I guess this is conditional. Okay. So if we just replace this, we get 4L T square on f xk minus f x star plus f x tilde minus f x star. Okay, now notice that we can combine this ffk minus f star with this term. So let's do that. We just simplify the expression a bit. Two t 1 minus 2lt. Yeah, so 2t times 2lt is 4lt squared. F xk minus f x star. And then there's a trading term that's 4lt squared f x snapshot minus f x star. Yeah, so far everything is just a standard, except that we use this variance reduction lemma. Okay, and now let's take let's put this into the context and then make this snapshot, the snapshot at the S iteration of the outer loop. And let's take the full iteration, full expectation. Yeah, actually, let's do that in the next next page. Then on the left hand side, we have expectation of x. Take full expectation and sum up everything for k from 0 to n. Okay, so let's sum up the entire inner loop of the iterates. So recall that in the last page we got this. This one is smaller than xk minus x star minus 2t 1 minus 2lt minus fx star, and then plus 4lt square fx tilde minus fx star. Okay, so let's sum up everything for k equals to 0 to n, and also take full expectation over everything that we've had so far, over xk, over all the randomness of this inner loop, and over everything in the outer loop. So we'll see that Once we do that, we'll see that we've created a telescoping structure that a lot of this xk minus x star got canceled out. So in the end, we get e of the expectation of xn. So this is the end of the inner loop iterations. Okay, smaller than e of x0. So x0 is the starting point of this inner loop iteration. I guess minus 2t 1 minus 2lt. Then there's a summation of f of x k minus f of x star. With an expectation that's put here, and then plus 4lt square, the expectation of so since we f x tilde remains the same for the entire iteration, for the entire inner loop iteration, so we simply have multiplied the whole thing by n. So n is the number of iterations that we have in the inner loop. So we have x tilde minus fx star. Okay, everything seems right? So now notice that we are notice that at the end of the day, we're randomly selecting one particular iterate. So notice that this expectation include the randomness of selecting the next iterate. So this xk actually becomes so you can say that this is the same as the expectation of I guess n times the expectation of f of x s plus 1 tilde. So recall that in the algorithm we are choosing this. Recall that in the algorithm we're choosing this x tilde s plus 1 to be a random sample from each one of the iterates. Okay, so since this is now the average of the performance of each one of the iterate, so then choosing one at random will give us exactly the same thing as the 1 over n times the summation. Okay, so this is where they apply the from the algorithm how to update the outer loop snapshot. Okay, to see that for sure, let's no. So here's what it is. Choose t at random, right? So from every single one of these iterates. Okay, now if we organize things a little bit by moving the middle term to the left hand side, then we get the following inequality. Okay, and we get that this is smaller than the expectation of x0 minus x star. So x0 is actually just xxs, right? Since we're initializing the inner loop from the previous round of snapshot, plus 4 L t square n, right? 4L t square n. Then the expectation of f x tilde s minus fx star. Okay, so now let's apply the strong convexity of f. So let's so if we apply the strong convexity of f, in fact, this is also the M Polyak Lojasiewicz condition, which is implied by the M strong convexity. We can bound the first term. We can bound this one with objective function values. We can bound this with 2 over m of the suboptimality. Okay, recall this is simply the definition of the PL condition, and then I'll copy the remaining thing over. Yeah, so we're reusing a lot of things that we have already learned before about strong convexity from the first couple of lectures. And now these two can be combined since both of them are on this. So we get 2 of 1 over m plus 2ln t square expectation of fx tilde s minus fx star. So let's inspect what we have gotten here. Okay. So this one is larger than 0, so we can drop it, right? So we can simply throw it away. Okay, and then what we have is that the expected suboptimality of the next iteration of snapshot and the expected suboptimality of the current iterate, right? And well, there are coefficients here, but let's move things around and then write this recursive equation. So this implies the expectation of fx tilde s plus 1 minus fx star is smaller than just by dividing this over to the other side, we get 1 over m t 1 minus 2 lt times n plus 2 lt over 1 minus 2 lt expectation of fx tilde s minus fx star. Okay, so all we have to do next is choose this parameters t and n appropriately such that this term is minimized. So we want to make this as small as possible. So as long as we can make this smaller than 1, then we have a strictly smaller than 1, then we have linear convergence. But in particular, we want to choose this such that such that this one is small and this capital N is not too big. Okay, so let's go back to see like what is the choice of N. N is chosen to be proportional to the condition number, and this learning rate is chosen to be 1 over L. Okay, so if we substitute this into this recursive formula, then we get that this one is equal to 2. Okay, so that concludes the proof of the outer loop. But notice that this relies very strongly on this variance bound, right? So provided that we can get this this variance bound, then the proof is complete. So also notice that this analysis uses only tools and exclusively the tools that we have learned before. Properties of strong convexity and how to make use of the iterations and make use of the definition of convexity and strong convexity to construct a telescope sum structure. Okay, so let's now maybe take a look at how we can maybe analyze the variance. To begin, it's useful to recall that what we've learned before called Bregman divergence. So the Bregman divergence is a linearization gap, basically. So at any given point x, okay, so this is y, and this gap is a Bregman divergence. So it is defined in this case. So let me define the Bregman divergence to be fi. Yeah, actually, let's make this x. Let's make this x star. Okay, so the Bregman divergence of x at x star is equal to fxi minus fx star minus the x minus x. So notice that the Bregman divergence is a convex function. Also, since fi is L smooth, gi is also L smooth. Now let's see the gradient of gi at x. X. So recall that we've learned that the Bregman divergence is convex in its first argument. Then the gradient. So the gradient has an interesting structure when you choose the point of reference to be x star. So so this is a constant in x. This is a linear function in x, and this is a convex function in x. So the gradient of the Bregman divergence is equal to the difference of the gradient at x and the gradient at x star. Okay, so recall another thing that we learned before. Descent lemma, right? So we talked about this in the first lecture. We talked about the when we talk about the gradient descent, which says that suppose you move towards a gradient direction of a convex function that's L smooth, then you are able to sufficiently like reduce objective function value, which says that say g I of x minus the t of gradient of f t of gradient of g gradient of gi at x. This is smaller than gi of x minus 2l gi x squared. So if the t is chosen to be smaller than 1 over l. Actually equal to something on the order of 1 over l. Okay, so what does it say? Suppose we pass in the gradient calculation here. So this if we pass in the gradient calculation here and notice that suppose we substitute the gradient, this is actually x x star. Wait, let's actually substitute this into here to see. So if we so the gradient of gi of x over here is equal to, according to this calculation, is equal to the difference of the gradient of fi x minus the gradient of fi at x star. Okay. Now the difference between these two Um, um, so we'll get fi x minus fi x star minus fi x star x. And on the left-hand side, we have since this is defined on the right-hand side, we can get f of x star minus f of x. Yeah, can someone help me a little bit here? I'm so suppose we plug in this into GI of into the definition of GI of x. We should be able to write it as something that's connected to f star. Oh, I see. Here's what we used. So we're actually using the fact that this Brakman divergence is always non-negative. Okay, so we're using the fact that this is non-negative, therefore we are getting this 0 here, right? So then we get this minus gradient of fi of x minus gradient of fi of x star squared. Okay, divided by 2L. So what this implies, if we move this to the left hand side, we get gradient of fi of x minus gradient of fi of x star square over 2L is smaller than fi x minus fi of x star minus gradient of fi of x star transpose x minus x star. Okay, so let's now sum over the different summits, I from 1 to n, I from 1 to n, and divide everything by 1 over n. Okay, if we do that, we get f of x minus f of x star, which is suboptimality, minus x minus x star, and the gradient will become the gradient of f at x star. So for unconstrained problems, this is 0. For constrained problem, and by the first order optimality condition, you can show that for all the feasible solution x, this term is greater than 0. Using x star is optimal. And on the left hand side, like we have we just have this, which is the sum of the gradient differences and relative to x star. Okay, so let's keep this and then replace this with 0. So for this, we are essentially getting a bound from the descent lemma itself and the property of the Brakman divergence, that we can bound the property of the individual gradient using the difference of the objective function value. Okay, so now with this we're actually ready to prove the lemma about variance reduction. So so this is what we are trying to prove, right? We're trying to upper bound this quantity from above using the suboptimality. So recall that this Vk is equal to the gradient of f, a randomly chosen ik at evaluated at xk, subtract f of ik at x tilde, which is a snapshot, and then plus the gradient of f at x tilde. So this is the definition of vk. Okay, so let's apply the condition, the inequality that x plus y square is equal smaller than 2x squared plus 2y squared. Okay, in the using the vector form, smaller than 2x squared plus 2y squared. By just applying this inequality and then substituting this equation for vk, then we can get the 2 times expectation of gradient of fik xk minus 1 minus gradient of fik x star. So let's subtract the gradient x star and then add it back. Okay, so since previously we now have a bound of this we now have a bound of the gradient difference compared to that of the optimal solution. So let's try to get it out from this inequality so that we can apply the star equation that we had before, right? So by applying this inequality, we can get a snapshot minus gradient of fik at the x star minus gradient of f at x star. Okay, so notice that this is the so gradient of f at x star is equal to the expectation of the gradient of fik when ik is joined uniformly at random at f tilde. So if we subtract out part of the expectation, then we can we can throw that part away while only getting upper bound of the overall expectation. So fik xk minus 1 minus gradient of fik x star plus 2 expectation of gradient of f star minus right. We can create this upper bound by using the fact that the gradient of f is actually the expectation of the gradient of fik here, and then we can apply apply the star from the previous page. Which upper bound the differences of the gradient with the objective function, and the expectation will the expectation over ik will create the sum of the gradient over all the summons of the individual summation form, and that will finally gives us a bound of 2L times we're applying the 2L, so 2 got multiplied in front, so we have 4 times the f at xk minus f at x star plus 4L f at x theta minus f star. By just applying this this star equation from the previous page to both this term and this term, and that concludes the proof for the lemma, and hence concludes the proof of the entire analysis. All right, so I guess I used up all the time I have today. So we'll continue with the remainder part of the discussion on other algorithms in adaptive gradient and other things. Here and combine that with a discussion of the ADMM algorithm, which is a useful algorithm to deal with non-smooth optimization problems where each components will have a proximal operator that can be more easily solvable, together with various examples of using ADMM. All right, yeah, thank you all for coming, and see you next Monday.